right, so this is the last talk of the day. So I know how you feel. But, we're going to see a bunch of really cool stuff. So please try to keep your eyes open. So this is my cat. His name is URIs. Super nice cat. So very quickly about me. So I do cryptography research for a company called Fastly. They helped me come here today. So thanks to them. And what's more relevant for what's going to follow is that for the past 15 years or so, I've been maintaining a project which is called jedisct1, which is all about securing DNS. So at the beginning, it was just one protocol to encrypt DNS traffic. And then eventually, it became an entire ecosystem with software to run on servers, clients, more protocols, and more importantly, it's a global network of free public resolvers, mostly run by individuals, and also not just servers, but relays to anonymize connections. So yeah, this is a project that I've been maintaining for a while and that I keep contributing to. And so I run a bunch of DNS servers and some of the infrastructure for this project. And one day, and of course, it always happens over the weekend, I got an email from one of my cloud providers saying, hey, your balance is running low. Which was weird because I thought I paid for the month just a couple of days before. But it was the weekend. I had more interesting things to do. I just wanted to avoid service disruption. So I was like, well, maybe something went wrong. Let me just pay. And well, it's going to be up and running again. The next day, same thing. Your balance is running low. Shit. Something is really wrong here. Well, so it was the weekend. I was with my girlfriend. I had more interesting things to do. I just wanted to solve that very quickly. So I did what anybody would do in 2025. I downloaded all the HTTP logs. I sent everything to ChatGPT, and I asked, what's going on? And sure enough, ChatGPT told me, well, there's a shitload of traffic coming from one specific IPv6 network, all with the same user agent, and hitting just a bunch of endpoints. I was expecting something more interesting, but yeah, good enough. So I blocked everything, and everything went back to normal. This is an oversimplification, but that's essentially what happened. All right, cool. Well, what did I just do? Just send a lot of private data for a service which is all about privacy to ChatGPT. Like client IPs and everything they did on the different services. This is all sensitive information, right? You shouldn't do that. Because it contains a lot of interesting information, starting with IP addresses. An IP address is obviously private information. This is a very easy way to correlate what you've been doing across multiple services. With just a request to an ISP, it's possible to identify you. So if you're an axe murderer and you don't use a VPN to buy access to kill people, you're going to go to jail thanks to your IP. So don't do that. So of course, an IP address is something you should not disclose to random third parties. And HTTP logs are worse because they contain IP, but also everything that happened on a specific API or website or whatever. So everything you did in addition to who you are. So not good, not something you should disclose to random third parties like ChatGPT. But wait, in order to do what I wanted, just know what I should block to avoid this attack, ChatGPT doesn't know the real information. Well, ChatGPT shouldn't need the real information. What ChatGPT has to do is trying to find anomalies, identify patterns. If I just send fake IPs and fake URLs, ChatGPT can still reason about that. ChatGPT can still tell me, hey, there is this set of IPs, which is sending a lot of traffic compared to all the other IPs. even if this is not the real IPs. And then if I have a way to map back the fake IPs to the real ones, I can block the real ones. So that's the idea. And same thing for URIs. So, OK, so we should start encrypting everything before we send that to ChatGPT or whatever. And of course, this is what I did. So let's start with IPs. How do we encrypt an IP? And this is where things get interesting. Because this is what we need. We need the process to be reversible. I send a fake IP, and then ChatGPT is going to send me one of the fake IPs, and I need to revert that to get the real one. We need that to be consistent. If I encrypt the same IP twice, I want the same fake IP so that ChatGPT can reason about that. I want that to be compact. Ideally, if I encrypt an IP, I want another IP as an output, not some binary blob. I want that to be fast and secure, obviously. So how to encrypt an IP? Well, if you look at what people are doing in the industry, this is all terrible. Well, if you ask lots of people, would you encrypt an IP? The response would be, well, I'm going to use ASGCM, because this is what they use in TLS. So ASGCM is like the universal answer to encrypting anything. Well, it's not a good option for many reasons. One of the reasons is that ASGCM is non-deterministic, which means that if you encrypt the same IP twice, you get two different outputs. For what we're trying to achieve, that doesn't work. Game over. There are other reasons why it sucks. You start with an IP, and what you get is something like a 44 bytes binary blob that you have to encode in base 64 hex or whatever, so you get something ginormous compared to an IP, which doesn't look at all like an IP, so your LLM might be confused. And there are other reasons not to use that, like usage limits. So terrible answer. All right, something else that people do is hash the IP. The problem is that the IPv4 address space is pretty small. It's very easy and very fast to brute force. So not super useful. Well, I'm going to hash an IP, but I'm going to include a key. So problem solved, right? Well, first, this is super slow. This is very slow to encrypt something which is super small, just a fucking IP. The output is going to be at least 32 bytes of binary data that you have to encode if you want to represent that as text. A lot of overhead for that. And, well, another problem is that this is not reversible. You can't take a hash and find the IP. So, well, not good. All right. Common practice is to change the last byte of an IPv4 address to a 0. Well, this is encrypted now. Well, no, this is terrible for many, many reasons. First, within a /24 subnet, well, this subnet can represent just one household, one person, one company. It represents a specific ISP, a very accurate geographic location as well. So this is not hiding much. And just given the traffic, somebody observed, if you send a small subset of IPs to an ISP, and you tell them, hey, can you identify the IP having this traffic at this specific time, it's very easy to identify you. So that doesn't really work. And what about IPv6? You can truncate an IPv6 address as well, but where? So yeah, a lot of people do that, saying that, oh, this is a way to comply with GDPR. Not at all. All right, so we need something better. Some kind of specialized encryption system specifically done for IP addresses. So this is one of the things I've been working on. This is called IPcrypt. So there was already something called IPcrypt. It was a system designed by Omason. It was a small block ciphers for IPv4 addresses originally. Very quickly, some practical attacks have been found, and the author said, well, it was just a toy cipher, don't use that. There was a bunch of discussions on mailing list about finding a replacement, but nothing concrete happened after that. So we are going to talk about a different IPcrypt, which is a specification. This is an ITF draft, which supports IPv4 and IPv6, because as of today, well, every piece of software is assumed to be supporting both IPv4 and IPv6. It has some strong security guarantees, high performance, and some people are already including that in their software, including Datadog and PowerDNS. So this is a set of 4 algorithms designed to be optimal for security and speed, and also for ciphertext expansion. So 4 different algorithms: IPcrypt ND, NDX, deterministic, and PFX. Let's start with the first ones, ND and NDX. This provides non-deterministic encryption. So this is a little bit like using AES-GCM, but this is much faster. It's also much more compact to encrypt an IP, even an IPv6. The ciphertext is going to be only 24 bytes, and you get very high usage limits. And also, compared to AES-GCM or traditional generic ciphers, there is something when you use AES-GCM which has to be unique every time you encrypt something. This is called a nonce, and if you repeat a nonce twice, the scheme fails completely. With IPcrypt ND and NDX, it doesn't fail. It degrades very gracefully. All you can learn from this is that an IP was seen more than once, but you don't learn anything about the IPs themselves. So much more secure, faster, more compact. But this is non-deterministic. So this is great if you need to store IPs in an encrypted way to maybe later decrypt them, but not for what we're trying to achieve with ChatGPT. So just about IPcrypt deterministic. This is another variant, which is, as the name implies, deterministic, which means that if you encrypt the same IP twice, you get the same output. The output, in this case, is an IP. So there is no ciphertext expansion. You get an IP as an input, an IP as an output, just a fake IP. The way it works, well, imagine that you have a sorted list of all the possible IPs covering IPv4 and IPv6. You shuffle everything. You get the same amount of elements in another list, just shuffled. So you have this bijection between IPs. So it's very easy to get the fake IP given a real one, and then revert the process. No expansion, and the way it was shuffled is the key. So this is essentially how encryption using AES on a single block works. And IPv6 addresses fit on 16 bytes, which is perfect for this primitive. So essentially, IPcrypt deterministic is just AES on a single block. So it can be faster using AES. All right, so it has some nice properties. Of course, it's compact. What you get is an IP. And what's cool is that beyond ChatGPT, you can use that with any tool that expects an IP. So any kind of log analyzer or log storage service, well, you can use that to encrypt your IPs. You don't get a binary blob, you get IPs. All right, there is a problem right here, which I probably wrote there. Yeah, the random permutation doesn't preserve network hierarchy. In the case of the attack that I saw, it was an attack from Facebook. It was actually not intentional. It was a bug in the infrastructure, but whatever. I got a shitload of traffic coming from Facebook. So it was not coming from one specific IP. It was coming from a subnet. And the problem is, if I use IPcrypt deterministic, I encrypt different IPs that look related. You can see the IPv6 addresses on the left right here. They look pretty much the same. But after encryption, the output addresses look completely different. So there is no way that ChatGPT can tell me, this attack comes from a specific network. Because all it sees is completely different IPs that looks on different networks. So maybe what we need is something called prefix preserving encryption. All right, introducing IPcrypt PFX, which does exactly that. So how does that work? Well, maybe we can start looking at the example first. So we get the same Facebook IPs on the left. And what we can see on the right is that the prefixes look the same on the encrypted IPs, but the end doesn't look the same. So essentially, if the plain text IP, the original IPs, have common prefixes, the fake IPs, the encrypted ones, are going to share a common prefix as well. So just looking at this, ChatGPT can tell me, well, this attack seems to be coming from this network, which is 2607F8, blah, blah, blah. So it's able to spot patterns coming from networks. Of course, this is not the real network, but it can still reason about hierarchy. So this is what prefix preserving encryption provides. So how does it work? Well, the idea is that first we add a little bit set to 1 before the real IP. And then we're going to encrypt bit by bit. We're going to start with the first bit, and we are going to derive a bit from a key, from everything we saw before that bit, and that's it. So for the first bit, we are just going to derive this from a key and the hard-coded one that we saw before. All right, we get some output that only depends on the key in this case. Now we're going to move to the second bit. Of course, we start with the top bit of the IP address. So we're going to move to the second bit. For the second bit, what do we have before? We have the 1, and then we have the value of the previous bit, which was the top bit of the IP. So we combine that with the key. We get something that looks random. This is going to be the encryption of the second bit, and so on and so forth. By doing so, as long as we have the same prefix, the same bits in the IP, we're going to produce the same output. But once we have two IPs, and once they start to diverge, then all the prefixes are going to be different. So that's the idea. Maybe this is a little bit more self-explanatory or not, I don't know. But we have 128 bits in an IP to cover IPv6. So we start with just the 1. And then we compute some random function using just this one and the key. We get some bits. And the next step is going to be computing an encryption. Well, not an encryption, but some random function using the 1 and the first bit of the IP, and so on and so forth. So that's how it works. So we need to have some kind of random function, something that takes a key, some input, and then spit out a bit. Everything in IPcrypt is based on AES. And AES is not really designed to be a pseudo-random function. However, there is a way to do it. There is a construction which consists of using AES or anything else that looks like a block cipher. So in this case, it's AES with two different keys or two halves of a key. And then we give them the same inputs. And we get different outputs, and then we XOR the outputs, and we get something that behaves like a pseudo-random function with nice security properties. It achieves 128-bit security. And that can be super fast, because this encryption process, when we encrypt the different bits here, can be parallelized. All the bits computations can be performed independently. And on modern CPUs, CPUs can perform multiple AES operations simultaneously. So this is something that can be super fast because it can run in parallel. All right. So IPcrypt PFX has nice properties. It's prefix preserving. It's format preserving, which means that if we have an IP as an input, we get another IP as output. It's deterministic. So it's super useful to do any kind of network analysis, like the case that I had with Facebook. So it can be useful for abuse detection as well. You don't need the real IPs to mitigate DDoS attacks based on this, traffic pattern analysis, and so on and so forth. So there is a specification, there is a research paper, an online demo, and implementation in many, many languages, including Zig. Just a quick comparison of the different variants of IPcrypt with the different properties that you get to cover different use cases. All right. So well-defined primitives. What about URIs now? Because in HTTP logs, we have IPs, but also URLs, including referrals. So maybe this is something we want to encrypt. The same way we use IPcrypt PFX, maybe we can do something that's prefix preserving as well. That could be useful, because in that case, we can send some fake URLs to ChatGPT that correspond to, /wp-admin, /API, or /.git, all the shit that common security scanners are hammering your web servers constantly with. So we can send fake versions of that, get some output from ChatGPT or whatever, and then revert that to get the real path. So can we do the same thing as what we did with IPcrypt PFX, but for URLs? Enter URIcrypt. So it works pretty much the same way. Well, the idea is pretty much the same, except that for IPs, the unit was a bit, but for URIs, the unit is a component. Like in this example, we have 5 different components. The scheme is not included for practical reasons. But then we have /delimited components. Not just slashes, we can have question marks or dash signs or different things that separate components. So essentially what we want. So of course, there is an ITF specification as well for that, and a Zig implementation, of course. So this is an example of URIs. So you can see that they share common prefixes. They all share /API/v2, and 2 of them share a longer prefix, API v2 users. And when you look at the encryption of that, you see the same properties. They all share a same prefix, which corresponds to the API v2 part, and the 2 last ones have a longer prefix than they share as well. So how to do that? Well, here's an intuition of how we could do that. We split everything into different components. That's easy. And then given the master key and the content of individual components, we derive multiple keys. So 1 key per component. And then we encrypt these keys with, we encrypt the components with each of these keys. And yeah, so sorry, a key depends on the master key and everything that was before a component. Yeah. In order to do so, we use something called a ZOF. ZOF is a cryptographic primitive that looks a little bit like a hash function. It can take an input of any size, but you can get an output that looks like random of any size as well. So this is very useful. We can use that to derive a key from the prefixes of every component and from a master key. And we can also use that to generate some stream that looks like random of a length that matches the length of every single component. And then we combine this random stream with the components themselves to get their encryption. And before every component, we have to add a couple bytes so that we can decrypt this. But it comes with a nice property, which is the fact that an encrypted URL is not something we can tamper with. It's impossible to modify something without this being detected during decryption. So this is useful against any kind of active adversary, but also against LLMs. Why? Because LLMs work really well when you have very small sequences of tokens. Like if you have an IP, it's going to reason about this IP, it's going to output this very IP at the end. That works really well. Now, if you have a pretty long sequence of things that don't look like common words or anything, that looks like garbage, that looks like encrypted something, well, sometimes they hallucinate. Sometimes they remove some characters. Sometimes they add characters. So what you get is not exactly what you sent. So they tend to screw up sometimes. So by using this authentication tag, well, when we get something from an LLM, we can verify that this is legit. This is something that we previously encrypted. And this is very useful because if we use this to block entire subtrees of a website or an API or whatever, we want this to be correct. We don't want to screw up because some bits were lost in translation. So that URIcrypt provides this guarantee as well. So here's another example with different API endpoints. And same thing, we can see that whenever prefixes are shared in the encrypted version, we have a prefix that's shared as well. And given the length of the prefix in the encrypted version, you can infer the length of the prefix in the original URI. So that works to detect patterns. All right, so now we have two very useful tools to do privacy-preserving log analysis. And the workflow works like this. We collect HTTP logs the old way. We encrypt all the IPs that we can find. We encrypt all the URIs that we can find, including referrers. We can send encrypted logs to ChatGPT or any kind of tools doing analytics. We get some insights. And in the report that we get, of course, all the IPs are completely wrong. All the URIs are completely wrong, but we can decrypt everything and then block the right stuff. I wrote a tool to do that. It's called logcrypt. This one is not in Zig. Sorry for that. I have to write a Zig version of it. But it does that. It supports a bunch of very common log formats like Apache and all these things. So yeah, a quick tool to encrypt the URIs and your IPs. All right. But do we always need AI? Well, probably not, especially for very specialized tasks like this one. So another project I'm working on is called BotBreak, which is a privacy-preserving abuse detection tool. So it's made from scratch to work on encrypted data, encrypted logs, where all the URIs and IPs have been encrypted. And it tries to detect patterns of common attacks, like a specific IP trying to hit a lot of different endpoints. This is something trying to scan your service, or a lot of different IPs that hit your service, but just on one specific endpoint. That could be a DDoS. So it tries to identify some common attack patterns, but there is nothing hard-coded, no hard-coded string in that. Like, it's not trying to detect bots because it's named OpenAI or whatever. It's just based on patterns. So it's just using a bunch of boring statistics. There is no AI right here, but statistics that work. So you can see the paper here, and there is a website. And the goal of this website is that this is a service that I want to provide to anyone who wants to protect their websites. They can send encrypted data, and the website can tell them, hey, I have found something suspicious here. Maybe you should block this network or this user agent or whatever for this specific amount of time, so that you have to pay less money for your cloud providers because you don't have to handle so much shit. So yeah, this is called BotBreak. This is a work in progress. But back to the Facebook story. So jedisct1 is using a bunch of different cloud providers. And another one is Fastly. I use Fastly for one of the DNS services. And I was like, well, when I got hit by Facebook, I took at one specific provider, but maybe something bad happened on Fastly as well. The problem is that on Fastly, I don't have HTTP logs. Well, this is something that you can enable if you want to. Intentionally, on my service, they were disabled because this is a service about privacy, so I don't want to keep data if this is something I want to disable. However, I still can get a bunch of useful information about my service. For example, how much traffic I got at a specific point in time, and how much traffic from different POP, and how much traffic went to specific servers, backend servers, and so on and so forth. So in order to spot something weird, well, what I can do is maybe go to the web interface and then click everywhere, look really closely at every single graph and try to make sense of all of this. This is painful. And this is where actually agentic AI can be useful. I can just tell an AI model, hey, this is the set of APIs that you have access to, do your stuff. So in order to do so, what we have to use is something called an MCP server. So by default, an AI agent is not going to do much. It's going to take some text as input and output text, and that's it. If you want to be able to call APIs or read files or perform any kind of action, well, the software you use to communicate with your AI provider is going to inform the model, hey, I have a bunch of tools that you can use. If you use this specific convention, I'm going to spot this and call some API for you. So this is what MCP servers allows you to do. And there is an MCP server for Fastly, which allows AI models to interact with your Fastly account and your Fastly services to retrieve any kind of statistics and inspect configuration and do anything that you would do in the web interface or using the API directly. So you can just ask, what does the traffic look like for this service? And then the AI is going to try the best APIs. It can try to maybe come up with something interesting for you. All right, so this is essentially how the call flow works for an MCP call. So on the left, we have a user asking for something to their AI client. The AI client is going to forward this to the AI provider, and there is going to be some communication. At some point in time, some kind of call to an API or a different tool is going to be necessary. So this is going to be forwarded to an MCP server, which is going to perform the actual API call, and then forward that to the AI client and eventually to the user. What's important to see here is that there is a lot of communication between an AI provider and the MCP server. An AI provider is never going to call an API directly, but the AI client is never going to call an API directly either. So the AI provider is essentially the middleman who knows all the parameters that will be used to call an API, and who knows all the responses for API, because this is what it's going to use to summarize the output of the API before returning that to the user. So if I ask my MCP server, hey, please list all my Fastly services, for example, well, it's going to use the MCP server, but because we have OpenAI or Anthropic or whatever as the middleman driving all the conversation using this MCP protocol, well, the AI provider is going to learn a lot of secret data, like all the IDs, because this is required to call the actual APIs. And these IDs might be secret. And then from the API, I can get interesting insights, such as, oh, the backend server whose IP is 1234 is sending much more traffic than other backend servers. This is very useful information for me as a user. However, this is also secret information. I'm using a CDN specifically to hide the real IP of my servers to protect them against attack. But now OpenAI and Anthropic and all these AI providers know about these IPs. Well, maybe we can trust them, but still that's annoying, right? Well, this is something we can actually mitigate, and this is built in the Fastly MCP server, because I've been working on this. So essentially what it does is that whenever you ask for something and it hits the MCP server, it's going to scan your request for sensitive data, like credit card numbers and SSH keys, access tokens, API keys, IPs, anything sensitive. And before before sending something to an AI provider, so a response to an API call, it's going to encrypt all the sensitive data. So the AI provider is never going to see the real credit card numbers, even if, as a user, you entered an actual credit card numbers in your original request. And then we get a response with the fake credit card numbers, fake IPs, fake whatever from the AI provider. And before sending the response to the user, we decrypt everything. So the user just sees the real card numbers and IP numbers and everything. So we get encryption, which is completely transparent. So that's how it works. The problem is that what we saw before works well for IPs and URIs. However, how do we encrypt credit card numbers or phone numbers? Because, yeah, they use very specific formats. A credit card number is 16 characters, but all the characters have to be digits. So there are a bunch of tokens that have to respect a specific format. So can I like generalize what we saw before with format-preserving encryption? The idea would be that, hey, I want to encrypt this. This is the alphabet that I have. Like I need to use only digits or only alphanumeric characters or whatever, and I need 10 digits. So I want the output to be 10 digits, just like the input, so that the credit card numbers look exactly like a credit card number after encryption. So can we do that in a generic way? So that would be very useful for the MCP server, but there are many, many applications of this. So of course, this is called FP, format preserving encryption in a generic way. And there are two standard ways to do that, which are called FF3 and FF1, which have been standardized by NIST. And FF3 has a pretty bad history. The first attacks were discovered in 2017, and NIST said, shit, that sucks. So let's increase the parameters a little bit, and we should be safe. Well, a couple years later, it was proven that it was not safe at all. The mitigations didn't work. So NIST said, oh shit, oh shit, oh shit. And just a couple months ago, NIST completely removed that from the standard. It's completely broken now. Don't use that. All right, so FF3, it's over. Okay, so what's left? The only option left is called FF1. Problem, it's super slow. It's still okay from a security perspective, but it's fucking slow, especially if you have long inputs. So if you just want to encrypt SSNs, that's okay. If you want to encrypt anything else, that's a little bit longer. Credit card numbers are okay-ish, but anything else, it's fucking slow. Okay, plus it's not easy to implement. So that would be a really great primitive to have if it were fast. But in practice, people don't use that much except in finance because, it sucks. It's way too slow. All right. So there's been a paper called FAST, which is much better. It's not broken. The cryptographic system is pretty sound, even if it's based on the same ID as FF1 and FF3, it's not broken. What's more interesting is that it's much faster than FF1, especially for long inputs. So super cool, right? The problem is that it's essentially just a research paper. There is no clear specification. There was a lot of details left to the reader. It's not easy to understand and implement, and you have to carefully choose parameters. For this reason, until very recently, I was not aware of anybody having written an open source implementation of that. So I did it. There is an implementation in C, in Go, and in Zig. So pretty cool. You can use any alphabet you want and encrypt an input of any length you want. And you get an output of the same length and same alphabet. And performance is not too bad. It's not fast. So it's called fast because it's faster than the rest, but it's not blazing fast. All right. There is something else which is fast, for real. And that you are probably using right now, because this is how the file system of Android is encrypted. So this is something called HCTR2. And this is length preserving, which means that in this case, the input is binary, the output is binary, so you don't choose the alphabet. However, you don't get any ciphertext expansion. If you have an input which is 100 bytes, the output is going to be 100 bytes as well. And this is very useful for encrypting file systems because file systems are encrypted block by block. A block is like 4096 bytes. And you don't want expansion. You don't want more bytes to encrypt every block because that would be messy and you would lose space. So you need something that preserves the length. So HTTR2 does exactly that. So as an input, it takes a secret key. It takes a tweak. A tweak is like the block number, so that if you encrypt the same thing in different blocks, you get a completely different output. And some message, so like a block. And you get an output which has exactly the same length as a message. And if you change any bit of the key, the tweak, or the message, the output changes completely. So that's a nice property compared to ASGCM and all these generic algorithms, because if you change just one character or just one bit in a file, the entire block is going to completely change. So it's very difficult to learn what you changed just by looking at the encrypted blocks. So nice property, no zero storage overhead. So that's nice. However, it takes binary inputs, but binary bytes, and outputs binary bytes. So that works really well for file system encryption. It's fast. The construction is pretty sound. But is there a way to reuse the same ID and the same basis and support arbitrary alphabets, like use HTTR2 to encrypt sequences of digits, for example? So maybe, and this is a paper I released about 2 weeks ago, which is HTTR2FP and HTTR3FP. And it supports any alphabet, any radix from 2 to 256. It's length preserving and format preserving. It's super fast. It's just as fast as HTTR2 if the radix is high. And of course, there is a Zig implementation. So it's super nice. There is still a limitation, which is that you must have a minimum length for your input, which depends on the radix. But that can be useful, for example, to encrypt file systems, to encrypt file names. In this case, the minimum length is not a problem. But if you need to encrypt something whose length is below that, well, just use fast or whatever you can. So let's talk about file name encryption. So if you look at a file name, well, all the file systems that I'm aware of have limits. Like a file name must have at most 255 bytes. You can create a file that has a name that exceeds this limit. All right. So if we use something that adds additional bytes after the file name, well, we have a problem because some file names can't be encrypted anymore. That sucks. So we can use format preserving encryption. That would work. We define the alphabet, which is all the characters that we can find in a file name. We apply FPE, and then the output is a valid file name. Looks easy, right? So we can even use HTTR2FP because the minimum of 22 characters is not a problem for file system. Well, we have a problem now. There are 2 limitations for file systems in modern operating systems. Well, a file name should not exceed 255 characters, but all these bytes actually should form a valid UTF-8 sequence. So if the alphabet that we define is all the bytes that could be found in a valid UTF-8 string, well, we're going to have an output which uses exactly the same alphabet. So that's super cool. However, it might not be a valid UTF-8 sequence. And how to fix that? Well, this is still an open problem. So I started to think about this a little bit, and this is just one approach. It's not perfect. It kind of works. I'm sure we can do much, much better. But the idea is to split the UTF-8 string into character classes, like character that encodes in just one byte, characters that encode in 2 bytes, 3 bytes, 4 bytes. And then within every classes, we do FP. So if we have a 3-byte sequence, it's going to be encrypted into another character that fits in a 3-byte sequence. By doing so, everything is still a bunch of valid UTF-8 sequences, and we don't have any expansion. The length is exactly the same as the input. It's not ideal. It's not fast. It kind of works. I'm sure we can do much better. So if you have ideas, I'd love to collaborate. And of course, there is a Zig implementation of that. But being able to do format preserving encryption on UTF-8 would be super useful for many use cases. So encrypted file names, of course. But if you want to encrypt your posts on X or whatever, well, right now, there are some tools to do that, but everything is going to be encoded using base 64 or whatever. So you can't hit the maximum limit that you would be allowed without encryption, which sucks. And actually, that would be useful for anything where the text is the input, and then you have limits, even in databases or whatever. OK, so to recap, we saw 3 types of encryption: length preserving, format preserving, which preserves the alphabet in addition to the length, and prefix preserving. So until very recently, all these things were super useful, but not used much besides finance, because they were slow or insecure, or because just people don't really talk about them. But now we have some pretty decent primitives with implementations in Zig. And you can find a bunch of links to the different things I've been talking about so far. And thank you. Before the drinks.
Before the drinks. Say we start with you. Actually, I have 2 questions.
Yeah.
The first one would be, have in the denial of service traffic you have seen coming to your services, have you seen any indication that this was an AI crawler for Facebook AI?
OK, no, that was not an AI crawler, spoiler. Well, it's not easy to make the distinction between AI crawlers and real crawlers, because they do pretty much the same thing. They are trying to hit some URLs that they already know about, unlike security scanners that are just trying everything in order to hit something. So no, it's the way people make the differentiation between AI crawlers and other crawlers right now is based on the user agent. So in this case, this is something you can use. In the statistic models I have in BoatBreak, maybe the distinction would be something it could spot. But there is nothing wrong about AI crawlers. A lot of people are like, well, we should block them because they suck. However, if you want people to visit your website today or even more next year, you should be indexed by AI crawlers, or your website would be invisible from the internet. So you want AI crawlers just like other crawlers. But what you don't want is any kind of crawler trying to send you a shitload of shitty traffic. If you get a ton of traffic and then your balance runs out in a day, well, no matter who is sending you that, you want to block that, right?
Yeah. Thanks. And the second question goes into the security of the prefix preserving URL encryption.
Yeah.
What I always wondered with the system was like, suppose you have a website with 3 URLs, and 2 of them have a very common component, and there's one which is different. If you now encrypt this with with your system, you would get 3 ciphertexts where 2 are a bit similar and the third one is different, right?
Nope.
So,
This is encrypted on a component level, but within a component, the encryption is deterministic. Let me get back to the slide on this. Yeah, a lot of slides. All right, maybe we can see this. I don't know if we can see that properly anywhere. So anyway, if you change just 1 bit in a component, the output for this component at the same location is going to be completely different.
okay, I mean, this is a good example because let's take the admin URL, and then there's this 2 users thing.
Yeah.
Can't you do? I suppose that somebody who wants to decipher the encrypted URLs knows at least the domain. So in practice, an attacker who wants to decrypt these encrypted URLs just scrapes your whole domain and then encounters these 3 URLs, 1 with admin and 2 with users. So can't you just use plain statistics to figure out that because the bottom 2 URLs share the same prefix and the first one does not, can you use this to make some statistics and finally decrypt those stuff?
Yeah, well, in this case, this is just a stupid DOS attack that you can detect using really dumb statistics. If you try every single possible prefix and compare to the outputs, this is just a brute force attack, and of course this is going to work by definition. You can use statistics to say, hey, I saw this set of encrypted prefixes a lot of time with shitty suffixes that don't match any real IP on my web server. So this is something shady. So somebody is trying to brute force my URLs, and you can block that.
Okay. Yeah.
Remember that there is this authentication tag in URIs, in encrypted URIs. So you have a way to verify that that was not tampered. But you can also just use this very small set of bytes within the encrypted URIs just to keep counters, as a key to keep counters. So you can see, yeah, there is somebody trying a lot of different suffixes within the same prefix, and that can be shady. Yeah.
Yeah. Okay. Thanks.
Yeah.
When analyzing IPv4 address, is there a way to avoid that the anonymized address runs into a blocked section of IPv4? Something that's restricted?
So it depends on what you're using. So if you use PFX, an IPv4 is going to map to an IPv4, and IPv6 is going to map to IPv6. For other schemes, there is the standard way to map an IPv4 into an IPv6. So we get a 16-byte representation of any kind of IP. And this is what all the other schemes are using. So if you have an IPv4 as an input for IPcrypt deterministic, for example, the output might be an IPv6, and the other way around.
I do like that it also works the other way around, which is fun.
Yeah.
Can I just check that for the URI, for example, for the domain, are you reversing it? So it's sort of postfix preserving for the domain and prefix for the root.
So the domain is just one component.
It's all one component. You're not doing
well, just one component. Yeah, yeah.
Okay.
Probably makes sense to reverse because it is a tree structure as well. So whatever data.example.com and users.example.com should probably also have the example.com prefix.
Maybe. I don't know if in practice that would be the best thing to do. I think this is pretty nice to just have a completely different output if you have 2 different domains. even if they are pretty close.
One example, one real-world example, for example, is the GitHub codespaces API.
Yeah.
Where if you spawn a code space, I think whatever it has got code.github.com or something. And for them, it would probably be really useful to see that only code spaces are sort of tagged. And
Okay.
this would be preserved. Like you will still see that it's whatever.code.github.
No, that would appear to us
That's
completely different.
not preserved right now, but it would be useful to have.
Yeah, okay, yeah, sure. Yeah. But you know, you can just replace, well, no, you can revert that, yeah. Yeah.
What exactly is hash encrypt hash, and how can it possibly work when hashing, unlike XOR, isn't reversible?
Hashing like XOR is not feasible.
Sorry, hashing isn't reversible. How can it work? Like, how can hash encrypt hash work, and what does it mean?
Oh, okay. It means that actually, in order to do length preserving encryption, you need to run multiple passes. It's not just a one pass thing. So you have to compute some kind of secret based on the key that you have and based on the content itself. So this is the hashing pass. So the output of this hash is going to be the key that you're gonna be using to encrypt the content. So we have two passes over the content. And then you do more hashing for authentication. So this is a generic construction that's used by a bunch of different things, including, but not limited to HTTR2.
I see, thank you.
Thank you. I actually didn't even know about length preserving encryption, so this was very enlightening. Question is, which file systems require valid UTF-8?
macOS, at least.
Oh, I didn't actually know that. Thank you.
Probably all of them. And maybe if the limitation is not at the file system level, it's going to be at the application level.
Okay, even application limitations.
Yeah, I guess the system on the Mac doesn't really care, but the Finder does, because it can't render something like that looks super weird.
I see. Thank you.
Drinks? All right, cool.
Thank you.
So a few things before you all run